Hello. In this video we're going to look at two classic examples of conditional probability, one with Venn diagrams and one with tree diagrams. So let's look at this first one. 80 students in a year group. Of these, 40 play tennis, 32 play soccer, 20 play neither. Illustrate the information in a Venn diagram. Well, the key thing here is that 20 play neither. So really there are only 60 students who are playing tennis or soccer or both. But we've actually got 40 plus 32, which is 72. That means that 12 of these 72 must be double counted. In other words, the intersection tennis and soccer must have 12 elements in it. So if we call the left hand one S for soccer and the right hand one T for tennis, we know there are 20 outside who don't play either, and we know there are 12 on the intersection. If there are 40 who played tennis and 12 of them are in the intersection, then 28 of them must just play tennis. And similarly, if 32 play soccer and 12 play both, then 20 must play just soccer. As an aside, we can see straight away, if 40 play tennis and there are 80 altogether, then the probability that a random person plays tennis is 40/80ths, which is a half. And the probability that a random person plays soccer is 32/80ths, which is 4/10ths or 2/5. Okay, and now we're going to use this to calculate some conditional probabilities. In part 1, probability of T/S means the probability of T given S, the probability that a random person plays tennis given that we know they play soccer. Well, intuitively, if we know they play soccer, we're actually talking about just the 32 students who play soccer. So of those 32, 12 of them also play tennis. So intuitively, the answer is 12 out of 32. Technically, the proper formula is the probability of T intersection S divided by the probability of S. The given condition is always underneath. And from this, the probability of T intersection S is 12/80ths divided by 32/80ths, and of course we get the same answer, 12/32ths. Part 2, the probability that a randomly selected student plays soccer given that we know they play tennis. We know they play tennis. We're not talking about all 80 of the students. We know that they are one of these 40 who play tennis. And of these 40, then we can see that 12 of them also play soccer. So 12/40ths or 3/10ths. In exactly the same way as before, the probability of S intersection T divided by the probability of T. Part 3 is a little bit more complicated. The probability of not T given not S. In other words, given that we know they don't play soccer, we know they don't play soccer, so it's not these guys. So the only people we're talking about are the 28 people who only play tennis and the 20 people who don't play either. So of the 48 who don't play soccer, 20 of them don't play tennis. So the answer is 20/48ths. Technically, this is the probability of not tennis and not soccer divided by the probability of not soccer. Well, not tennis and not soccer leaves these 20 people outside, so that's 20/80ths. And as before, we can see from the diagram, not soccer is 48/80ths. Intuitively is often the better way to do it. But if you do need to use algebra, then the key formula is the intersection divided by the given condition. So, part C, are the events independent? Well, we can see from above that the probability that a person plays tennis given that they play soccer is 12/32ths, and 12/32ths is 6/16ths is 3/8ths. However, the probability that a randomly selected person plays tennis is 40/80th, which is a half. These two are not the same. Therefore, knowing something about whether the student plays soccer does alter the likelihood of them playing tennis. This means that they are not independent. Similarly, the probability of soccer given tennis from above is 0.3, 12/40ths, but the probability of playing soccer by itself is 32/80ths, which is 0.4. So again, these two are not the same, therefore they are not independent. And the other way to do it, which is often quite popular, is to say that if they were independent, then the probability of the intersection would equal the probability of one multiplied by the probability of the other. But the probability of the intersection is 12/80ths. Does that equal 40/80ths times by 32/80ths? And the answer to that, clearly 40/80ths is a half, so the right hand side is actually 16/80ths, which is not the same as 12/80ths, therefore they are not independent. This second example really is a fairly complicated tree diagram, and it helps to understand the bigger picture and think of this intuitively rather than looking at hardcore formulae. I'll give you a chance to read it. I'd like you to try to draw this in a tree diagram, realizing that the question is set up as either men or women buying diesel or not diesel, and buying with credit card or cash. So I'll give you a couple of minutes to try to draw the correct tree diagram. What you should have realized is that the first decision is the customer a man or a woman? And then the information in the question tells us information about a man buying gasoline and a man buying diesel, and so on. You should have the first two branches like this, and then the last branch is credit card or cash, and then the last branch is credit card or cash. Okay, and now we can put the probabilities on. If 60% of the customers are male, then obviously 40% of them are female. 25% of the men buy diesel, therefore 75% of the men buy gasoline. Similarly, if 10% of the women buy diesel, then 90% of the women buy gasoline. A man buying diesel with a credit card is 40%, therefore with cash is 60%. A man buying gasoline with a credit card is 70%, therefore with cash it must be 30%. A woman buying diesel with a credit card is 30%, therefore with cash must be 70%. And lastly, the probability that a woman buying gasoline with a credit card is 80%, and so with cash must be 20%. And multiplying along the branches gives us the exact set of circumstances. So the very top branch, if we multiply all these together, 0.6 times 0.25 times 0.4 is 0.060. And this is the precise probability that a randomly selected person drawing up to the pumps is a man who buys diesel and pays by credit card. Continuing in this vein, we get 0.090, 0.315, and so on. So when you've completed it, the tree diagram should actually look like this. Another way of thinking about it is, instead of adding up to 1, we can think of it as adding up to 1,000. And of the 1,000 people who turn up, 60 of them are a male who buys diesel with a credit card, 90 of them are males who buy diesel with cash, 315 of them are males who buy gasoline with a credit card, and so on. And it's a lot more intuitive, I think, in a lot of cases. So the probability that a randomly selected customer will pay cash. Realistically, the cash people are every branch which contains cash as the end result. So starting at the top, we've got men buying diesel with cash is 90, men buying gasoline with cash is 135, women buying diesel with cash 28, and women buying gasoline with cash is 72. So altogether, of these 1,000 people, how many of them pay cash? And we just add up these numbers, or we add up their associated probabilities, and we get the same answer, and this is just 0.325. Every single one of these separate circumstances is mutually exclusive to every other one. There are no situations where a man buying diesel with cash also is a man buying gasoline with cash. They're all separate, unrelated events with no overlap, and therefore or simply means we add them together. That's the simple one. The next two are a little more complicated. The probability that a customer who gets diesel is female. Technically, the probability that it's a woman, given that we know they've bought diesel. The given condition, customer who gets diesel, so we know that they're a customer who gets diesel. Where are all the diesels? And it's these guys and these guys. 60 and 90 men and 12 and 28 women. Technically, the proper equation for this is the probability of the intersection, women and buys diesel, divided by the probability of diesel. So the probability of being a woman who buys diesel is these 12 and 28, or 0.012 plus 0.028. So this is 0.040 divided by all of them, 0.028 plus 0.012 plus 0.090 plus 0.060. Or in other words, these 40 over the 40 plus 150. So it's 40 over 40 plus 150, which is 4/19. And finally, the probability that a customer who pays cash for gasoline is male. A customer who pays cash for gasoline is male. We know that they've paid cash for gasoline. So who are these people? Cash for gasoline is this one and this one. So we're really asking the probability that the male, given that they bought gasoline with cash. Well, technically, according to the formula, that's the intersection, so it's male and gasoline and cash divided by the probability of gasoline and cash. Well, male and gasoline and cash is 0.135, and gasoline and cash, well, they could have been either male or female, so it's 0.135 plus 0.072, and that is 135 over 207. Now, of course, you could think of it pretty obviously. Of the 1,000 people who came in to the gas station, 135 were males who bought gasoline with cash, and 72 were females who bought gasoline with cash. So altogether, there's 207 people who bought gasoline with cash, and of those 207, 135 were men. So do use the formula by all means, but in most cases a more intuitive approach is probably easier to follow.